Hey everyone, this is Group 30, and today we'll be presenting our project on detection of AI generated social media text. This will be the flow of our presentation. I am Ananya, and before I get into anything, I want to ask you a question. Take a look at these two tweets, they are the same topic, format, and style. Just one was written by a human and the other one by AI. Can you spot the AI generated tweet? Well, the one on the left is the answer. And if you got it wrong or weren't sure, that's exactly the problem we're solving. Models like ChatGPT, Claude, and Gemini can now generate social media posts that are nearly indistinguishable from human writing. And this isn't just an interesting research problem, it has real consequences like fake news, coordinated opinion manipulation, and astroturfing at scale. All of this powered by AI that writes like a person. So, why can't existing detectors just handle this? Three reasons. First, they are trained on known AI models. The moment a new one appears, performance collapses. There's no retraining or update, so they're blind to it. Second, most detectors were built for long form text, news articles, and academic papers. Social media posts are short, noisy, full of slang and emojis, which is a completely different problem. And third, the literature is overwhelmingly English and single platform. Our dataset spans across 22 languages and 5 platforms. Existing tools simply weren't built for this. Which brings us to our research question. Can combining retrieval with LLM fine tuning improve generalization across unseen AI models and social media platforms?
So, with that central research question in mind, we now turn over to the data that will help us answer it. Starting over with the dataset overview, we use three datasets, each with a distinct role. Multisocial is a primary training corpus, a multilingual collection of over 472,000 texts from Twitter, Telegram, and Discord, spanning over 24 languages, labeled as either human or AI written by models such as GPT 3.5, Gemini, or Mistral. HCQ provides supplementary domain-specific question-answering style data, and adversarial QA is reserved only for evaluation, offering adversarial QA pairs to stress-test model robustness. One immediate concern in the data is class distribution. As you can see, the AI-generated text is at 87%, meanwhile the human-written text accounts for just 12.3%. This imbalance we will address shortly. All three datasets are unified through a six-step pre-processing pipeline. Starting with format unification and text normalization, we convert everything into a single JSON schema, clean platform-specific noise like hashtags and emojis, and normalize text to reduce surface-level variations. Next, label unification, where multi-class model-level labels are collapsed into a binary target label, such as 1 for AI-generated text and 0 for human-written text. Embeddings and retriever setup. The full corpus is encoded using a dimension 256 mini LM model, and a phase index is built on the training split for downstream retrieval. RAG variants. Each training example is prepared twice, one with retrieved nearest neighbor context and once as a prompt-only version without retrieval. Finally, evaluation splits. 5 test splits are created: standard, cross-model, cross-platform, adversarial, and short text to evaluate generalization across diverse conditions. Solving the class imbalance. Before balancing, the training set is 88% AI generated. Validation and test sets retain this natural skew to reflect real world conditions. To fix the training imbalance, we apply random undersampling in 4 steps. Sample AI text down to match the human count using a fixed seed for reproducibility. Rebuild the phase index on the balanced subset and regenerate both with RAG and without RAG training files. The result is a balanced corpus of 133,926 samples split equally across both the categories. The split for training will be 70% and 15-15 each for validation and test.
Coming to the architectural decisions that we made for this project, our system is built as a full end-to-end pipeline across three different stages. First is the offline data pipeline, which is also data preparation. Second is the fine-tuning that we did for training the models. And last is the inference pipeline. In the data pipeline, we pull from two different data sets, the multi-social data set and the HC3 data set. We unify them into a single corpus of around 133,000 records, and then we generate a 768 dimensional embedding using Google's Gemini Embedding 2 model. These embeddings are then fed into a FAS index built exclusively from the training split to prevent any data leakage into validation or test. For training, we follow two variants per model. We went with Llama 3.1, 8 billion instruct, and the Quen 3, 8 billion models. We fine tuned both these models with and without RAG context. For the models with RAG context, we use the embeddings generated from the training step to enrich every training example with its nearest neighbors. It created RAG augmented instruction data, which we then fed into the model during training, and then we fine tuned it. At inference, the two detectors operate as independent signals, KNN path and LLM path. The KNN path embeds the post, searches the FAIRS index, and returns a confidence score via a cosine weighted majority vote. The fine tuned LLM path, on the other end, receives only the raw post and produces its own independent prediction based purely on what it learned during training, with no neighbors passed at inference time. This entire inference system is served through a fast API backend with a web frontend for real time classification. The key design choices are as follows. The training embeddings were taken care of to prevent data leaking. The training data was balanced to have equal number of human and AI labels to prevent bias. The softmax loss was on the response only, not on the prompt or the RAG context. And two independent signals gave us a good holistic comparison of the model's performance.
Hello, my name is Sneha. And now let's deep dive into the specific LLMs that we used in this project. First, we start off with Llama, specifically version 3.1, which has 8 billion parameters. So, why was Llama used for this project? Well, it was trained with over 15 trillion tokens and not in just one language, over multiple languages such as English, Hindi, Thai, Spanish, French. And this kind of gave it a common sense understanding of these languages, which is crucial for multilingual social posts. The 8 billion version was smartly chosen because it's able to balance low latency with high reasoning capabilities. So your inference speed is fast and your classification accuracy is high. While training, grouped query attention was used because datasets like multisocial data have a high volume nature, and this is able to efficiently process that. It also improves the instruction following and has a larger context window, which is around 128K, thus allowing it to maintain memory. Because social media posts tend to be lengthy, the memory aspect is very important in this dataset. And as you can see, the performance speaks for itself. We have all the metrics being scored at true positive rate at 1% false positive rate, and for the standard scenario we have the score of 95.38%, while cross model and cross platform are at 99.53 and 99.95 respectively.
One of the models that we chose was the Llama 3.1 8 billion parameter instruct model. The reason we picked Llama 3.1 is because it is trained on a more broad and general corpus. It is more receptive to in context evidence, and because it is an instruct model, it follows the RAG instruction format very reliably. So we fine tuned the Llama 3.1 8 billion using QLoRa with rank 32 and alpha 64. We used the Unsloth library, and this was trained on an NVIDIA A40 GPU. The key design choice is that RAG is baked into training, not just applied at inference. For every training example, we query the FAS index and inject the top five most similar labeled posts directly into the system prompt. This makes sure the model learns to classify while simultaneously reasoning over the corpus evidence. To keep the model focused on the actual decision, we use response only supervision, which means that the loss is computed only on the final output token, which is either AI or human, and not on the prompt or the retrieved context. During inference, the model receives only the raw post with no neighbors injected. We extract the token logits for both the labels and apply a two token softmax to get a calibrated confidence score. This stands alone as an independent signal compared directly against the KNN baseline. What we found in our testing, and as is evident from our test scenario performance, was that the fine tuned LLM catches subtle stylistic and linguistic patterns, the kind of things that reflect how AI systems tend to write, whereas the KNN simply votes based on the nearest neighbors in the embedding space.
Moving on to our second standalone LLM detector, we utilized Quen 3 with 8 billion parameters. So, why Quen over other models? First, it's currently a state of the art performer for conversational text. It was a strategic choice for us because of its unique pre training. It was developed with a heavy emphasis on multilingual understanding and informal conversational structures, which is exactly the noisy environment of social media. We have non thinking and thinking modes. For this detector, we explicitly disabled the internal chain of thought reasoning as we wanted to test the model's gut instinct based purely on its fine tuned weights. This not only reduced the latency to about 1 second per post but also gave us a more direct and objective classification. Its tokenizer is highly optimized to handle the slang, emojis, and messy grammar we see on different platforms like X or Reddit, where standard models often trip up. And most importantly, Quen is incredibly sensitive to what we call the subtle polish of AI. So it is perfectly tuned to catch linguistic signatures in a chat like context where things get a bit too grammatically perfect. And looking at its performance, the results speak for themselves. We achieved a 94.95% true positive rate on the standard dataset, which is already quite strong. But if you look at the generalization on both the cross model as well as cross platform scenarios, it is very, very high. And this is because the model is so well pre trained on informal human noise, it is able to spot the contrast of AI polish even on models and platforms that it has never seen before. This proves that our reasoning based approach generalizes far better than traditional and statistic detectors.
Now let's move on to Quen 3 with RAG context. So as we previously saw with Llama, when RAG context was added to the LLM, it actually improved the results and gave better classification. Let's find out if that's the same when it comes to Quen. So Quen is built on a massive corpus which has around 36 trillion tokens, and this causes a densely packed internal knowledge base. So it already has enough context over multiple languages. So when a RAG context is added to it, it sometimes acts as noise and that kind of confuses the model. It's unsure if it should listen to its own internal weights that is built upon by its corpus, or should it actually follow the external retrieved text even if it may be right. That kind of causes this disparity between the two values, which is referred to as the quantization noise. This leads to poorer distillation and it's not able to fully assimilate the external context that's provided to it. Because of that, it could cause hallucinations or distractions, both of which falter the actual results of performance of this model. And that is very well shown in the results table. If you see in the scenario standard, the TPR at 1% FPR is actually lower. It's 93.07% here, and cross model and cross platform are also lower, which is at 94.54 and 99.73. So it is not a fact or a rule of thumb that adding RAG context always improves model classification. It also depends on the type of model you're using and the pre-training that's used along with it.
This is Aditya, and now we will discuss model comparison. We compared four model configurations across three increasingly different test scenarios. The test results tell a clear story about how RAG interacts differently with different base models. Llama with RAG is our strongest performer across the board, Adding retrieval made it more consistent, more robust, and better at generalizing. Exactly the outcome RAG is designed to produce. The reason comes down to how Llama processes external context. Llama is highly receptive to injected information. It treats retrieved passages as useful guidance and integrates them into its reasoning fluidity. RAG essentially fills the gaps the model isn't certain about, reinforcing its decision rather than disrupting them. Then why did RAG hurt Quinn? Quinn tells the opposite story. Without RAG, it performs well, but adding retrieval actually degrades its results. This points to a fundamental mismatch between Quinn's internal reasoning style and the RAG pipeline. Quinn appears to have a stronger, more rigid internal prior from pre training. When external context arrives, instead of complementing its reasoning, it competes with it, introducing ambiguity at exactly the moment where the model needs confidence. This is a critical finding. RAG is not universally beneficial. Its value depends entirely on whether the base model is architecturally or behaviorally suited to defer to retrieved context. A model that trusts itself too much will treat retrieval as interference, not assistance. So the real takeaway isn't just which model scored highest. It's that base model selection and retrieval strategy must be co-designed. Pairing the wrong model with rank can leave you worse off than no retrieval at all.
Hi, I'm Twissa and today I will be taking you through the demo of our social AI detector. Let me walk you through the interface first. We have a text box up top where we will paste the post that we want to evaluate, but we'll get to that in a moment. Below this, we have two detectors running side by side. On the left, we have vanilla KNN. It embeds our input, searches a FES index of thousands of posts, and votes based on nearest neighbors. It's purely similarity based, either on topic or on writing style, basically, whatever lands closest in the embedding space. However, it does not reason. On the right, we have our very own fine tuned Llama 3.1, which has been trained across a variety of texts, through which it has learned to pick up on subtle stylistic cues that go beyond surface similarity. So we have same input but two different approaches. Let's see what each of them predicts. I have a few examples for the demo today. Let's first try the one that has been generated by AI. So I've posted a post that we already know is generated by AI, and I also hit the analyze button. Here both detectors agree that it is 100% AI generated. KNN also found neighbors that are overwhelmingly AI labeled. The vote is unambiguous. The LLM independently reached same conclusion from what it learned during fine tuning. When the signal is this strong, you can see this formal structure, the hashtag, motivational corporate tone. That's the case where both approaches converge. This is the easy case, really. Now let's try the one that's actually interesting. This is a post written by human, and you can see that KNN has predicted it to be AI with 60% confidence, whereas LLM on the right has given the vote of it being a human written post. So we have same input, but we are getting opposite verdicts. KNN unfortunately got it wrong. It got neighbors that are close in embedding space, which happen to be AI labeled more, enough to tip the vote. It doesn't know why they are similar, it's just votes. It could be based on topic or tone, but it can't really tell the difference. The LLM, on the other hand, gets it right. It's picking up on what is actually making this human. If you go through it carefully, there is lowercase, the use of slang, then there are fragmented sentences, there are emojis, there's emotion. These are distinctly human signals on social media that don't separate cleanly in embedding space, but the LLM has learned to recognize them. No retrieve context, no hints, purely based on what it has learned during fine tuning. That's the difference between voting and reasoning. Thank you.